So one of y'all hit that start button.
I did.
Oh, you did? Okay. Alright, so this is factors affecting the rate of dissolving, making it mix together. That's what that means. Alright, so how can we increase dissolving, making it dissolve quicker? Alright, so we can increase the surface area, agitate it, so stir it, you know, if it was in a test tube, we could agitate it, which would be like moving it, heating it, or changing its solubility. Alright, so we're gonna go more in depth. Okay, so first one was increasing the surface area. So how do you increase surface area? You have to make smaller pieces. So think about it, if you were making sweet tea, which is gonna dissolve quicker? Tiny granules of sugar or big chunks of sugar? Tiny granules, obviously. Well, tiny granules is actually increasing the surface area, because now you have all the surface area of every single tiny granule instead of just the surface area of your large chunks. So crushing the solute, what you're dissolving into it, makes more surface area, which causes it to dissolve faster. So anytime you have smaller pieces of something, that's increasing your surface area. So turning crystals into powder, that's going to increase your surface area, thus causing it to dissolve quicker. Alright, so that's one way, increasing surface area. Alright, another way, is this the right mouse? No. Alright, is agitating it, so stirring it or shaking it. Obviously, you know, if you're trying to make some sweet tea at home, you're not just going to mix the sugar and the water and you're going to stir it. Alright, that's going to make it dissolve quicker. Alright, so stirring or shaking helps disperse those particles, so it brings the fresh solvent into contact with more particles, and that's why it dissolves. If you just have all the solute sitting at the bottom, it's not getting all your particles into contact with the solvent, and that's why they don't dissolve as quickly. So when you disperse it, it allows the solvent to actually come into contact with the solute, and that's why it dissolves quicker. So agitating it, stirring or shaking. Alright, heating it. We know that warm liquids dissolve better than cold liquids. So as temperature increases, our solvent molecules move faster. That's why we heat it, because now our particles are moving faster. So once again, those solute particles are going to come into contact with that solvent quicker because they're moving faster. So it's all about them coming into contact with it. Once they come into contact together, the solute and the solvent, that's when they dissolve. Alright, so if they can come into contact quicker, because they're moving faster, you know, higher temperature, more energy, moving faster, then they're going to dissolve quicker. Alright, and the last one, solubility. So the amount of a substance required from a saturated solution with a specific amount of solvent at a specific temperature. So sometimes it's just not soluble. You might have to add more chemical for it to actually dissolve. Sometimes you might have super saturated it. Do you know what that means?
Too much.
You added too much, and then it won't dissolve. So sometimes it just depends. Maybe you didn't add enough, or maybe you added too much. So it kind of just depends on the solubility of that chemical. Maybe it just doesn't dissolve at all. Maybe it's insoluble, and that's why it won't dissolve. So it just could depend on the solubility of that individual chemical. So 4 factors that could affect the dissolving of a chemical are those 4. Okay. Alright, so we're going to talk about, we talked about solutions, now we're going to talk about suspensions and colloids. Alright, so a suspension, what is a suspension? It's kind of like a solution, but it's a little bit different. So a suspension is when the particles are so large that if we let it settle, so we just let it sit, they would settle out. So like an example, like Italian dressing. If we sat there and shook it, all right, the particles in Italian dressing are going to mix all throughout. But if you let it sit, what's going to happen to all those particles in the dressing? They go down to the bottom. That's a suspension. Same thing as if I put mud in water. Did my phone die?
No, it's on low power mode. It's good.
Oh, okay. Alright. It's gonna die soon, probably. Alright, same thing as if I put mud and water. Alright, if you put mud and water and you mix it together, you get less muddy water, right? It's gonna mix together. But if you let it sit, the mud is gonna settle to the bottom. And eventually you'll have mud on the bottom because it's more dense, right? And you'll have the water on top. But then you could stir it again and it's gonna turn into muddy water again. And then you could let it sit again and it's gonna settle to the bottom. Alright, that's a suspension. Alright, a suspension is something that our particles are so large that they will settle out if we let it sit. Alright, so suspensions. Alright, versus a colloid, which can also look like a solution. Alright, but the particles in a colloid, alright, are intermediate in size. So we have solutions where our particles are so tiny that we can't see them. They all look like one. We have suspensions where our particles are large, and then we have colloid right in the middle. So a colloid looks like a solution, but the thing is that our particles are intermediate in size. So how we can tell is we can use the Tyndall effect. Alright, so we can shine some light, and that's my next slide, so I'm not going to get too far ahead. So the particles are intermediate in size between a solution and suspension. So some examples: aerosol sprays, milk, mayonnaise, fog. You guys drive, most of you probably, right? Maybe some of you don't. Alright, fog is a colloid. Alright, Jello. Lots of people are always like, what state of matter is Jello? Alright, well, Jello is a colloid. Alright, whipped cream. Alright, because here's what a colloid is. It looks like all one thing when you look at it. But if you shine light through it, which is called the Tyndall effect, if you shine light through it, so think about you were driving to school this morning. Maybe there's fog out. Imagine fog. You don't see, you just kind of see white fog. But when you shine your headlights through it, do you see particles?
Yes.
Like rain.
Yes, that is the particles that are in the air that causes the fog. But you don't see it till you shine the light through it. Those are the intermediate particles. The particles that are too big to be a solution, where we wouldn't see them, but not big enough to actually settle out to the bottom like a suspension would over time. That's why they're floating in the air. Same thing as Jello. If you shine a light through some Jello, you're probably going to see some particles floating in it. Alright, which is why it's not a suspension. Your Jello doesn't settle over time, but it's also not a solution. Yes?
So I have a really weird question. So with like thickened liquids, does it like, what is it?
What'd you say? What liquids?
Thickened.
Thickened liquids.
So
Okay.
we have a powder and you pour it in the drink and it dissolves into the drink and makes the drink thick. But then it sits for a while and all the thickness kind of goes down to the bottom.
So what do you
at
think
least-
that would be? Which one? Solution, colloid, suspension? If it settles.
Suspension.
If it settles, it's going to be a suspension
But
because
it
those
also
particles are
dissolves
too big. It will mix, right? It makes it thicker. But if the particles are too big that they'll settle over time, that's a suspension.
Like the particles don't settle, but like the water at the bottom gets very thick.
Well, that's your
water on top.
particles
Oh.
settling. Now, maybe not every single one. Some of them might stay, but most of them are settling to the bottom, which is why it's getting real thick at the bottom, and probably why you want to shake it or stir it some before you drink it, or not even drink it at all after that. You know those teas that people order? The first time I ever ordered one, the energy teas, they were like, Miss Dow, it tastes terrible because you're supposed to stir it. That's a suspension, because when they put that stuff in there, all that stuff is more dense. It just settles straight to the bottom, and you're supposed to stir it up before you drink them. And I didn't know that, so I started drinking it, and I was just drinking the straight energy stuff at the bottom instead of actually mixing it into the fruity liquid stuff that you're supposed to. So those are suspensions. If it settles, it's because your particles are too big. They'll mix, but they're gonna eventually settle down. All right, so Tyndall effect is how we can tell the difference between a solution and a colloid. All right, because it occurs when light is scattered, so it's bouncing off of those intermediate particles. So an example would be like your headlight beams on fog. All right, so colloids versus solutions, what we just said, is used with the Tyndall effect. So you shine a light through it. Through a solution, you're not going to see anything. But through a colloid, you will see the particles. Because what's happening is the light is bouncing off of those intermediate particles because they're not completely dissolved. And so that's how you can tell the difference between a colloid and a solution, is with the Tyndall effect, shining a light through it. Oops. Alright, so as a refresher, alright, solutions are homogeneous. They all look the same. Here's your actual particle sizes, very small particles. If we let them sit for a while, they're not going to separate. Solutions would not. They do not separate by filtration. So if we were to pour salt water through a filter, it's not going to separate, right? My salt water would go straight through because it's fully dissolved in the water. And it does not scatter light through the Tyndall effect. All right, colloids, remember those are our intermediate particles. Those are heterogeneous. Why are they heterogeneous? Think about it. Why is a colloid heterogeneous? Which thing up here makes it heterogeneous? Because when you initially look at it, it's not going to look heterogeneous. It's going to look homogeneous. What causes it to look heterogeneous? Joey? Yeah, the Tyndall effect. That light scattering causes you to be able to see those particles in it. Without using the Tyndall effect, it's going to look homogeneous. It's not going to look heterogeneous. All right, so our particles are intermediate in size if you compared the sizes here. It does not separate on standing. Those particles aren't big enough to settle. It still won't be separated by filtration. Think about if you had Jell-O, when you make Jell-O, before you put it in the fridge and it gets hard, you could pour it through a strainer. It's not going to separate. You're not going to be able to pull out those Jell-O particles. All right, it's still going to be a red liquid going through a filter. But with the Tyndall effect, with light, you will be able to see those particles in between. So that's what makes it heterogeneous. All right, and then suspensions, the biggest particles. All right, if you let it settle or sit over time, your particles will settle out because they are the largest particles. It can be separated by filtration. Think, if you have muddy water and you put that through filter paper, that mud is going to stick in the filter paper. The water will go straight through. That one can be separated by filtration. And if you were to put a light through muddy water, it's going to scatter light, but it's not going to be transparent, right? Think about it, muddy water, light's going to scatter, you know, it's not going to go straight through. It's definitely not going to be transparent. To put light through muddy water? No, but I can imagine. Yeah, I'm sure it's, yeah. So just a review there of the three. Good. And this is all in the slides, so you have access to this. You can always go back. And now it'll be on the video. Alright. Alright, I think this is the last thing. So solutes, they can be electrolytes or non-electrolytes. So remember, solutes are what we put in our solution to be dissolved. Alright, so an electrolyte is a substance that dissolves into water and it conducts electricity. What causes the solution to conduct electricity. So examples, any soluble ionic compound. Because what causes the electricity to be transmitted through the solution? Ions. So when you put that ionic compound into the solution, it breaks apart into ions. And remember, we talked about that last year when we talked about chemical bonding. I did the example for you with the light bulb. Remember we put the light bulb in water? And first I did sugar and I put it in and sugar did not work because sugar is not ionic. And then I put salt in water and I stirred it around and I put the light bulb in and it lit up because salt is an ionic compound. And when it breaks apart, it forms ions. And ions are what closes that circuit and causes the light bulb to light up because ions are what conducts electric current. So as long as you have an ionic compound or a highly polar molecule. So what a highly polar molecule would be is like maybe an acid where you have hydrogen and an element that is on the opposite side of the periodic table, because if it's highly polar, it means it has big differences in electronegativity. And so electronegative, the most electronegative element we know is fluorine, and hydrogen's way over there. So if they're on opposite sides of the periodic table, they're gonna be highly polar, just like ionic compounds are on opposite sides of the periodic table, because you have a metal and a non-metal. Well, if I have hydrogen and chlorine, opposite sides of the periodic table, they're very polar because they're very different. Remember, polar is different. Yes, Grace?
So like, what should I put, like highly polar is?
Just,
Like,
you can put elements that are on different sides of the periodic table, because they're gonna have, they're gonna be very polar if they're on different sides of the periodic table. If I had like nitrogen and oxygen, do you think those would be polar? No, because those are right beside each other on the periodic table, so their polarity is not gonna be very different, because their electronegativity values are close, because they're right beside each other on the periodic table. It would have to be elements that are on different sides of the periodic table. Alright, so a non-electrolyte is obviously the opposite. It's a substance that dissolves in water that would make the solution not conduct electricity. So this would be a solution that does not have charged particles. So like sugar, so our covalent compounds are elements that are made of combinations of nonmetals right there on the right side of our periodic table. Because they don't make ions. You don't have ions in covalent compounds like nitrogen monoxide or carbon dioxide. You wouldn't have those polar ions in those. So this next test, since we're going through a lot of content stuff, is gonna have multiple choice questions on it, obviously, because we're going through a lot more content. There will be some math questions, but it's definitely not gonna be near as math heavy as this last test was. Not all math like this last test. Okay. Alright, we're not gonna do that. And I think that's it. I think that's all we needed to go through. Yeah. That's the next set of notes. Okay. Alright, so let me make sure I went through everything that you need to be able to do your assignment for. Yep. Alright, so your assignment is this paper, okay? When you're done, turn it in. Other than that,